Welcome back, ladies and gentlemen. We're doing 3.4, velocity and rates of change. Okay, we're going to solve rate of change problems using derivatives. Okay, there's our assignment in the upper right hand corner, but here we go. Okay, now instantaneous rate of change. Now the second I say rate of change, hopefully something sparks in your brain. From way back in Algebra 1, as soon as we talk about rate of change, we started talking about that when we started talking about something else, some famous S word, slope. Alright, so basically we're going to have a lot of tie-ins to that through the course of this particular lesson. So here we go. For any function f of x, the instantaneous rate of change, which again slope, is f prime of x. Now we've already talked about the derivatives of slope, so this is almost a redundant statement. Rate of change is slope, and the derivative is the slope as well. So hey, by the way, did you know that the slope was the slope? Alright, anyway, that being said, at x equals a, so if we just pick any number for a that isn't a particular x value that we care about, the rate of change is, again, just plug a into the derivative, because again the rate of change is the slope, and the slope is the derivative, yada yada yada. Alright, so here's one thing, as it says here, that I had a hard time wrapping my head around when I first started learning this from what my teacher said, so I want to say it now before you start thinking it. Instantaneous rate of change, it's how fast something's changing at a particular moment, not that the change happens instantaneously. I spent a long time thinking, well, how can you go from 0 to 40 meters per second without going through all of the other numbers between 0 and 40? Whatever. But anyway, it just means, hey, how fast am I going at a particular rate of time? Not that the change is happening instantaneously. Hopefully that made sense. Alright, moving on to velocity, or instantaneous velocity. Again, basically velocity at any particular instant, not that velocity happens instantaneously. If we're given a position function where s is our position, and then that is going to be represented by some function with a variable t, the velocity v at time t is given by either you could say velocity equals f prime of t, because again we're just taking the derivative of the function, or if the notation suits you, if you just want to say velocity equals s prime, that works for me as well, because really that makes the same sort of statement. Okay, then acceleration. Okay, and from a previous lesson we know that acceleration is basically the derivative of velocity. So our acceleration is going to be, again, the derivative of velocity, or if you want to go back to the original function right here, we could say that the acceleration is the second derivative of the original function, or again, if the notation suits you, you can say acceleration equals s double prime as well. Alright, now velocity is important in a physics sort of point of view because it gives the direction as well as the speed that it's going. Well, I say speed because speed is how fast something is moving regardless of direction. Alright, so velocity is kind of a two-meaning sort of thing, and speed is a single meaning. That being said, speed is given by simply taking the absolute value of the velocity function. Alright, so there it is. So whatever you get for velocity, take the absolute value, and you got yourself speed. Alright, now a great thing about being able to derive various formulas off of a starting formula, a position formula if you will, is that a single formula like that gives you an awful lot of information if you derive all the right formulas. So here we go. A particle is moving along a number line, so that its position is s equals 4t squared minus 5t plus 7. Okay, now for whatever reason the book decided not to give units on these problems, but I'm going to pretend that they are in meters and seconds to help with clarity so we can put labels on these things, so hopefully it makes a little more sense when we say a number. Alright, that being said, what's this thing's displacement? And that's the distance from the starting point. Just where did I start, where did I end up? That's your displacement over the first 4 seconds. So basically our displacement is going to be my position at 4 seconds minus my position at the starting time, which is 0 seconds. Alright, so basically I'm just going to plug in a 4 into this thing. So 4 times 4 squared, etc. 5 times 4 plus 7. Okay, then minus my position at 0 seconds. Well, that one's pretty easy to figure out, because if I plug in a 0 into here, the first two terms cancel out and I'm just with the 7. So minus 7. What's nice is those 7's cancel. So basically what I have here is 4 squared, which is 16 times 4, which is 64. Minus 5 times 4, of course, is 20. If you're not sure about that, check with your nearest third grader. And then subtracting those two, we get 44. And again, here's where I think units come into play. And we're talking position here, so the position is in meters. So this is simply 44 meters from our starting point. So 4 seconds later, we're 44 meters away. Alright, so then, well, what's its average velocity? Well, velocity, alright, is basically just delta s over delta t, so difference in your position over the difference in time. Okay, well, delta s is basically what we just figured out here because we're still talking about the first 4 seconds. If I would have changed the time period there, I'd have to do a new calculation, but since I didn't, I can just keep my 44 right there. Okay, clearly, this is 4 seconds for my delta t. From 4 to 0, I think we can count that as 4. And quick little division right there is 11. And again, unit-wise, I think it's important to consider the velocity here, because that's meters on top because we're talking position. Time, we're talking about seconds right here. So this is 11 meters per second as our average velocity. Alright, continuing on with this basic problem, which is actually a series of problems, but here we go. I want to know now its velocity when t equals 3. Well, I know its average velocity was 11 from the previous problem, but I don't know. That's just an average, so maybe at 3 seconds I might have been going a little faster, a little bit slower, so let's figure that out. Okay, now again, this is a position function, and my velocity is going to be the derivative of the position function, so in this case, it's going to be 8t minus 5. Alrighty, so then basically there I just plug my 3 in there, so that my velocity equals 8 times 3 minus 5, and that's 24 minus 5, and that's 19. And again, because I'm talking about velocity, I'm talking about meters per second. So definitely I was going faster there, so my average is considerably lower than what I was doing at 3 seconds in. Okay, what's the acceleration when t equals 3? Well, again, since acceleration is the derivative of velocity, we just go back to our velocity function right here, 8t minus 5, take the derivative, and that's 8. Okay, now notice we're left with no variables whatsoever, so I don't care what time we're talking about, our acceleration is always going to be 8, so it's simply 8, and again, probably easier if you're used to physics, but the units on acceleration, given the units that we are using right now, is meters per second squared, so basically meters per second per second. And there's our acceleration. Alrighty, continuing our analysis of this particular situation. When does the particle change direction? Okay, well, it's going to change direction, and if I'm changing direction, I'm going to consider velocity, because velocity, again, gives me both our basically direction and magnitude, or speed, if you will. And so, basically, my velocity at some point in this thing might be negative, and later on it might be positive, or vice versa. And if I'm going from negative to positive, well, I have to go through 0. So basically, when does the particle change direction? That's going to happen when v equals 0. So what I want to do now is look at my velocity function, and we figured that out earlier. Velocity is 8t minus 5. Okay, so basically, again, I want that to be 0, so I simply set 0 equal to 8t minus 5 and solve, and pretty quickly I get t equals 5/8, and t is in terms of seconds. So 5/8 seconds into this guy's little trip is when he changes directions, so pretty early on. Okay, then if I want to know where is the particle when s is a minimum, okay, well, I can kind of use the fact that I know what this thing looks like if I were to graph it. Okay, clearly it's a quadratic, and if I graph this thing, I'm going to have a parabola. So basically, whenever I'm talking about parabolas, minimum or maximum values always happen at the vertex of the original function. Okay, so basically that's what I want to know now, the vertex. Alright, and believe it or not, we've already got half of it. Alright, our 5/8 seconds is basically the x-coordinate, or in this case the t-coordinate of the vertex. So basically what I need to do is plug in t equals 5/8 into the original s function. Okay, so doing that gives me s equals 4 times 5/8 squared, etc. And yes, this is going to be kind of a nasty number, but we can cope because we're cool like that. Plus 7. Okay, doing a little calculator button pushing and whatnot, I get an answer that looks a whole lot like 5.4375, or if you prefer, that is 5 7/16. So basically what's going on here, and guess I should put labels on this. Those are meters for both of those. So, whichever of those you like better. Okay, so just to get a visualization of what's going on here. Okay, the position function, okay, again, pretty obvious. When t is 0, this thing works out to be 7. So this guy actually starts over here to the right at a position of about 7. And then for 5/8 of a second, this guy is going, well, maybe it's not obvious right now, but if my position where s is a minimum, at some point during my trip I worked out to be about 5.4 meters as far as my position. So somewhere, there's my 5 and 7/16. So basically, here's where I started. 5/8 of a second took me back to here, but then after that, again, I changed direction. So I know at that point I took off and started going this direction. And I only changed direction once, so I know the rest of my trip I'm taking off over here to the right. So that's what this guy's basically doing. That's what all this information has kind of let us know. Alright, now granted, you probably don't spend a whole lot of your time sitting around thinking about particles moving left and right on a number line. But that is a popular thing to ask on an AP Calc exam, so it's very possible in the somewhat near future, about a year from now, you'll be taking an exam that has a question something like that on it. Okay, probably more realistically, you may have at some point in your life thrown a ball in the air. I almost guarantee it. Okay, but anyway, its position is given by this particular function. Okay, the 6 is, in case you're not sure, basically your starting height. The 72 is your initial vertical velocity, and the -16 is a number in this equation that has to do with gravity pulling the ball back down toward the Earth. Okay, now if you're in physics, you're probably used to seeing a different number there, but that's because we're measuring things in feet now instead of in meters. If it was meters, you'd be using a 4.9 or possibly a 5, depending on exactly what you were doing. Alright, but anyway, what's the ball's velocity as a function of time? Well, first of all, again, here's a position function, so the derivative of that is going to give me my velocity function. So in this case, here's my derivative. 6 goes away, the 72t becomes the 72, and then the 2 comes out in front, gives me a -32t. Alright, so there's my velocity function. Okay, then how high does the ball go and how long does it take to get there? Realistically, I think it's easier to find out how long it took to get there first. Alright, because quite honestly, I've got my velocity function right here, and I know if the ball is going up, it's going to come back down, and at the top of that flight, velocity is going to be 0, because effectively it stops for just that brief millisecond worth of time before it comes back down. So again, all I really need to do is set velocity equal to 0, so 72 minus 32t equals 0, and then we just got to solve that. So now I'm going to move the 32 to the other side and get 72 equals 32t, and a quick little division gives me t is 2.25 seconds. Alright, so 2.25 seconds, it gets to the top of its flight. And then how high does the ball go? Well, now that I know that, I know that I can go to my position function, again, which is realistically just a height function. So then my position is going to be 6 plus that time where it stops going up, 72 times 2.25 minus 16 times 2.25 squared. Alright, a little calculator button pushing later, I should get my position, my height, is 87 feet in the air. Alright, continuing on. Okay, I'm asking now, when did the ball reach half of its maximum height? Well, don't overthink this, but we just figured out that its maximum height was 87 feet, so half of 87 is 43.5. Right? And the question is when, so I'm trying to figure out t, and so there it is. In our equation, and again the 43.5 is a height, which is what s is representing, so basically I just set 43.5 equal to the function that I have, 6 plus 72t minus 16t squared. Alright, now I've got a quadratic, so I can either bring the 43.5 to the right, or I can smash everything over to the left, depending on your personal opinion. I'm going to do the least amount of work here, and then have to deal with a negative, but whatever. Just make a choice and run with it. So 0, and I'm going to write this in descending order so it looks a little bit nicer. -16t squared
plus 72t, and subtracting 43.5 gives me a negative 37.5. Okay, now quite honestly, maybe that's something that's factorable or something like that, but I wouldn't dream of even trying. So basically, what I'm going to do is put this in the quadratic formula, and I'm going for a decimal. Okay, with these numbers like this, quite honestly, and realistically, if you've ever thrown a ball in the air and said, hey, how long did it take? And somebody said, oh, well, it was 13 plus or minus root 75 over 13, that probably wouldn't mean much to you. So as I do this in the quadratic formula, I get myself a decimal. I get two answers. I get t equals 3.898 and some other messiness, and then 0.6011 and some other messiness. So depending on the amount of rounding you're asked to do, I think nearest tenth sounds pretty good to me. We're going to go 3.9 seconds and 0.6 seconds. Okay, hopefully you're not too curious about, well, there's two answers, or at least you're not thinking too hard about it, because, hey, if the ball throws up, it's got to come back down. So there's the two times. The 0.6 obviously is when it's going up, and then the 3.9 is a little while later as it's coming back down. Alright, now a follow-up to this is how long was the ball in the air? Alright, well, the ball was in the air. Again, we're talking about its actual height. Well, but how long was it in the air? So basically this is the time when the height is equal to 0. Alright, so basically I can just take my original function, put a 0 right there for s. So 0 equals what you see right there, 6 plus 72t minus 16t squared. Again, I think this is a perfect time to use the quadratic formula and not try to mess around and try to do any factoring and any goofiness like that, just because the numbers aren't very nice. And so the quadratic formula later gives me, again, two answers, as expected. T equals negative 0.08 and some other messiness, 18, whatever, and then 4.5818 and some other messiness as well. Okay, well, how long was the ball in the air? I hope negative time doesn't make a whole lot of sense. So basically, we're going to throw that guy out just because it's nonsensical for the scenario we're actually looking at. So this is what we've got here. So as a final answer, again, depending on the rounding directions you're being given, but I'm going to give it a tenths, and that's 4.6 seconds. So from the time it was released to the time it hit the ground, 4.6 seconds. Alright, moving to a new problem. If you're given a graph, kind of a, well, graph of position versus time, as it says here, s versus t. Alright, here's the position of the particle p moving on a number line. Alright, fair enough. Again, probably not what you spend your Saturday nights thinking about, but again, AP Calc seems to like this. So here it is. Alright, so at time 0, I was at 0 position, so I was at the origin, and then at 1 second, I'm at 2, etc. Alright, so the question being asked here, part A at least, when is P moving left, right, or staying still? Okay, well again, if I'm starting at 0, basically here's where point P starts out. Okay, and 1 second's worth of time in, my position, so I'm basically, this number line here is my position, in case that's not obvious. Alright, 1 second in, I'm at a position of 2, so I started at 0, and I made my way over here to 2 within the first second, so obviously I'm moving right. So when, so from 0 to 1 seconds, I'm moving right, but I might be moving right later, so I'm going to leave a little bit of room there. Alright, next little chunk of time, from 1 to 2 seconds, my position was 2, and then it's still 2. So he's just kind of camping out, so that's my standing still. So from 1 to 2 seconds, he's just staying still. Alright, now from there, I'm going from a positive 2 position down to a negative 2 position. So from positive 2 over to negative 2, that's what I did in the next little chunk of time. And clearly that's going left. So from 2 to 3 seconds, I'm going left. Right? Once I made it to negative 2, I kind of chilled there for a little bit. Notice my position stayed at negative 2. So again, I'm just kind of hanging out. And this is from 3 to 5 seconds, standing still again. So, and 3 to 5 seconds. Okay, lastly, my last little stretch that shows up on the graph, from 5 to 6 seconds, I went from negative 2 to negative 4. So I got bored sitting around here, and I went left a little bit further to that spot at negative 4. And so that goes in my left category. So, and that was from 5 to 6 seconds. So there's where it's moving, or at least the direction it's moving. Now the velocity and speed is something else we can figure out here. And one little piggy point is where they're defined, and there's something that we have to watch out for as we do this, but it's relatively minor, but I will include it in what I do here. Alright, so again, velocity, remember, basically is a change in position divided by the change in time. So basically what we can do here is just derive this information off of the graph. For instance, from 0 to 1, my position went from 0 to 2, so in this chunk of the graph, my delta S is 2, and my delta T, time that passed, was 1. So I'm at a positive 2 over 1 as far as velocity during the 0 to 1 time frame. So I can have kind of this part of the graph shaded. The where it's defined thing is because when I'm just starting, I'm kind of at 0, and then I kind of take off moving. So basically I'm not defined at the endpoint here. I'm also not defined at the endpoint at 1, because as I reach 1, I'm moving at 2 feet or centimeters per second, but then as I get past 1, we're sitting still. So I'm not exactly defined at 1, some kind of a change is taking place. So that's where the defined thing comes into play. Basically your endpoints are going to be open circles. Okay, that being said, continuing on from the 1 to 2 second time frame, again my position goes from 2 to 2. So again, my position change is 0 over the 1 second worth of time, so my velocity is 0, so I drop down here and have from 0 to 2 as my velocity right there. Okay, now from 2 to 3 seconds, okay, my change in position went from 2 to negative 2, so that was a change of 4 in a negative way over 1 second. So my velocity looks something like that. Alright, next chunk of the graph, I've got from 3 to 5. Again, that's a standing still, so it's a 0 velocity from 3 to 5. So a long kind of chunk right there. Okay, my last little chunk, I went from negative 2 to negative 4, so we changed in a direction negative 2, and that just took 1 second worth of time. So for my last 1 second worth of this particular trip, my velocity is negative 2. Alright, so there's your velocity graph. Alright, lastly, we want to do a speed graph. Now remember, speed is simply the absolute value of the velocity. So kind of looked at the velocity graph that we just did. Okay. So from the 0 to 1 second, we had a velocity of 2, and the absolute value of 2 is still 2, so basically that part of the graph stays exactly unchanged. The next chunk of the graph, from 1 to 2, our velocity was 0, and the absolute value of 0 is still 0, so that chunk of the graph stays the same as well. However, the next chunk, we were at a velocity of negative 4. But again, speed, I don't care about direction, so the negative is meaningless from that point of view. So I really have a speed of 4. So instead of being at the bottom edge of the graph, this guy jumps up to be the top edge of the graph when we're talking about speed. Okay, the 3 to 5 being standing still at 0 still plays out exactly how it did on the previous graph. But then again, since I'm at a velocity of negative 2 here, my speed gets absolute valued to be a positive 2. So then my speed graph looks like this. Basically, if you do a speed graph and have anything below in the negatives, then something's wrong. But anyway, there it all is. Again, as always, I hope it made a little bit of sense, and ask me in class. I'll see you there.